Audio Jungle. Audio Jungle.
So we'll write two types of waves. Okay. What are the two types of waves? These waves are compression waves, and another one is expansion. Okay. This compression will have again two types called normal shock and oblique shock. And this expansion wave still called as a expansion fan. Okay. This two only. It's a non-isentropic this is isentropic. Okay. I already explained about normal shock, so now this is the time of for the oblique shock. So it is very clear. Oblique shock is the part of the compression wave. Okay. In the compression wave, like word only you can understand compression. Compression means there is the rise of pressure. Expansion, there is the drop of pressure. If there is the rise of pressure, then velocity will drop. Expansion where the pressure, compression where the pressure is what rising, so velocity will drop. Similarly, expansion in the sense there fall of the pressure means velocity will be increasing here. So there is the difference. Okay. So expansion fan, expansion wave, I will explain later. Let me finish compression. So in the compression itself, normal shock already I have finished, and that properties and all you have seen. Okay. So there is no doubt about now the formulation and the concept behind the normal shock. Everything is what done, and we had seen the numerical also. We'll talk about oblique shock. We'll talk about oblique shock now. Oblique shock. All right. So I explained that time normal shock perpendicular to the flow. If any object is what placed, then in front of the object, that shock will be formed. If the flow is what supersonic, then shock will be formed, and that shock will be called normal shock. Why it is called normal shock? Because that object was placed perpendicular to the flow or normal to the flow, and hence the formation of shock was normal shock. Just relate with the oblique. So oblique shock, if I am saying, then it means it is not normal shock. Obviously, it is with some angle to the flow field that shock will be formed over the object. Okay, it is attached shock. This is the attached shock. So I will show like that diagram for the oblique shock. I will say this is the object. Okay, this object is what not exactly perpendicular, it is with some angle. Okay, it is with some angle, and this is the object. You can say this is the wedge here placed, and where is the flow field? This is the flow field. Check it out. This is what flow field. This is the flow field. Okay. So with this flow field, any one center line you can draw with this flow field. Okay, with this flow field. Now if you check, the object is what making angle with this flow field. Yes or no? This object is what making angle with the flow field. All right. So in this case, whatever the shock will be formed, that shock will be oblique shock, and that formation of the oblique shock will be like this. This is the oblique shock. Okay, this is the oblique shock now. All right, this is the oblique shock now. And if you check the flow pattern over this, after this formation of the shock, then how that flow pattern will be. So you just see the flow pattern here. Okay, and this flow pattern will be like this is the ahead to the shock and what happened behind the shock, so that flow will be turned because the object plane is what inclined to the flow, hence whatever the flow again it will regain the like, because this object is what making some angle, so obviously this flow will not go and pass through this object, obviously it is not possible, so this flow will turn parallel to the plane of object. So this is the object plane, and once flow will pass or behind the shock, when the flow go, then it will follow the parallel path, parallel to what? Parallel to the plane of object. So this is the plane of object. You can say this is the plane of object. Okay, this is the plane of object here. This is the plane of object. Okay. So this flow will be now get parallel to the plane of object everywhere. Here also parallel to the plane of object. This is the plane of object. Now, so all the flow will be turned like this only. Okay, anywhere if you draw the flow pattern, suppose here also I am drawing. So this flow will go parallel to the plane of the object. All right, everywhere. In fact, here also if you draw, it will go parallel. So this is all about the oblique shock. Okay. Now this is the thing, and how that shock will be formed, why the shock is forming. So everything, it is just like a normal shock. In normal shock I explained there is the rebounding of the air particle or fluid particles, and that rebounding particles is what colliding with the upcoming fluid particle, hence there is in front of the object one thin surface will be created because of the collision of the particles, and it is called normal shock. So same thing will happen here also, only one difference, now the object is not perpendicular to the flow, hence we don't have normal shock here. The object plane is what making some angle with the flow field, hence that oblique shock, that normal shock, now it becomes oblique shock. Oblique shock in the sense now it becomes having some inclination. Okay, normal shock, if I say what is the mean of normal shock, so suppose this is the flow pattern here, this is the flow pattern, this is what the normal shock, this is what normal shock, yes or no, this is the normal shock, and after this again the flow will be like this one. Okay, this is what normal shock. And when it was formed, when there is the one object placed, suppose this is the one object here, it is placed, this is the one object placed, and this is the flow field. Okay. So because of this normal orientation of this object with the flow field, so for that reason whatever the shock will be formed, that shock will be normal to the flow field like this. But now this object is what inclined, check here, this object is what inclined now with the flow field, hence whatever the shock will be formed, it will be with some angle. So you can mention here, if you want, you can write the line like similar thing like what about the normal shock? The normal shock wave, a compression front normal to the flow direction. There is special case of oblique shock wave. What is the special case? This inclination, it becomes perpendicular, then it will be called normal shock. So normal shock itself, you can see special case of the oblique shock. Okay. So that inclination, that angle I will show you here, then it will be more clear to you. So I can say, now another diagram I will draw. I can say, suppose the upper part of this object I will draw. So similarly, you can consider downside also. The upper part only I am drawing so that it will be easy for me to draw every time. So this is the upper part of the object. Okay, this is the upper part of the object. All right. And if you check here that because this is the solid surface, so I am just giving a hash line here. Okay. Now whatever the flow is what coming, take this up. Let me do another color for this object. This is the object. Okay. Now we have a flow field here. See, this is the flow coming towards the object. Okay. And now for this object, let me remove this part. Fine. Now check for this object, upper part of the object I have shown here. So now here we will have a oblique shock. Let me give another color. So this is the oblique shock formed here. This is the oblique shock. Okay. Oblique shock formed here. And now whatever the flow is what coming, that flow will be like, I will show the flow pattern here. I can see now this is the one flow and the stream. Okay. So now after the shock, this flow will be parallel to the plane of the object. So it is like this. Similarly, this like this. Similarly, this like this. All right. This is what all about oblique shock. Okay. Done. Now, so I will show the inclination. So inclination will be like this only. Check. I can say whatever the angle of this object or wedge, it is called theta. It is called theta. All right. And whatever the angle formed by the oblique shock here, it will be called as theta. All right. Again, that separate diagram I will draw because this inclination, that understanding of this inclination is what very important. Okay. I can say somewhere here, this is the object. So this object half portion I am showing you inclined object. So this angle will be theta for the object, and suppose oblique shock is what formed here. This is the oblique shock. So whatever the angle formed here, it is from the horizontal theta, and this angle will be theta. Okay. All right. So I can say here the beta. Beta is nothing but called as a shock angle. What it is called? Why it is shock called shock angle? Because this is nothing but oblique shock. This is nothing but oblique shock. So this oblique shock shifted from the horizontal to the angle beta, and theta is nothing but, what is the theta? Theta is called as flow deflection angle. Why it is called flow deflection angle? I will tell you. It is called flow deflection angle, or it is also called, I told you this is the object, but many times I have used the word called wedge. Okay, this is also called wedge. Okay, inclined wedge. So this inclined wedge angle is theta. And why it is also called flow angle, flow deflection angle, because flow will be deflected by this angle theta only. See here, the flow is what deflected. This flow is what deflected with this parallel to the plane of wedge. And what is the parallel uh, plane angle from the horizontal? It is theta. So similarly, whatever the downstream line, this line here, the same will have a same angle. What that angle? That is theta itself, because it is going parallel. Okay, this is parallel. Everywhere it is parallel, so obviously this formation of angle will be same for both from the horizon. All right, so I hope this one is clear. So basically this oblique shock, so it's a compression wave. It's a compression wave. It's a non-isentropic, non-isentropic. Okay, and you can say it is a it is a compression wave inclined inclined at an angle to the upstream flow. I explained what is the upstream and downstream last class, yes or no? So this is all about oblique shock. All right. If I say non-isentropic, so all the isentropic relation what we have, you cannot apply across the oblique shock. That's the mean of it. Yes or no? That's the mean of it. Okay. All naturally occurring shocks in external flows are oblique. Okay. Whatever the naturally occurring shock wave in external flow, it is always oblique. That normal shock chances are very less. All right. Now I said why it is the uh, like a special case of oblique shock. So you can say like this is the object here. See, this is the object or wedge here. Okay, and this object is making angle from the horizontal is theta, where the shock is what forming. Now this is what shock, oblique shock formed. Why? Because the it is like inclined to the flow field. It is equal to cross straight line, but okay. All right, and this angle is nothing but theta, and this is what oblique shock. In bracket OS, in short I will write oblique shock. If you check, if beta is 90 degree, then this oblique shock will be normal shock. Yes or no? Means from the horizontal, if this is what theta, which is 90. Okay, and if the flow field is what like this, so when you will get 90 degree, when the flow field is what like here only this, and the object is what, when it is shock is what making 90 degree from the horizontal, that means object is what placed like this. You can say object is what placed like this. Then it will be 90 degree, 90 degree to the flow. Yes or no? So that is called normal shock. So normal shock already you have seen how it will be formed. A similar kind of normal shock, oblique shock will also form, but here it will not be a normal to the flow field NHW normal shock. It will be with some inclination, and that inclination is called beta. Beta is called shock angle. For the normal shock, this beta will be 90 degree, but less than 90 it will be oblique shock. Okay, less than 90 it will always be oblique shock. So like I explained to you two things, that expansion corner or expansion fan and compression. So I will show you here two diagrams, so here you can understand easily. I can say here this is the normal surface, you can say, and now this surface is what inclined like this. Okay, the surface is what inclined, you can say like this only. The surface is what inclined now like this, and the same thing with the surface now, and this is also inclined, but it is like this. Try to understand that compression wave and expansion wave, how it will be formed. Check. Now this is one corner, this corner. Okay, there is the name of this corner. What is the name of this corner? This corner called as compression corner. What it is called? It is called compression corner, and this one is called expansion corner. Okay. Now, see, just for understanding, I am explaining you so that it will be more clear to you. Understand it should be very clear, right? If this is the corner, okay, if this is the corner, and obviously this corner and this surface will be making some angle, and this angle called wedge angle, which is nothing but theta. And here also from the horizontal, this is also making angle, which is called theta downside. So here, because it's a compression corner, so what shock will be formed? That shock will be oblique shock. Okay, that shock will be oblique shock. So we just say this is oblique shock, and this oblique shock angle from the horizontal is theta. Okay, what about this? And what about the uh, like expansion corner? Because this is the expansion corner, so expansion fan will be created here like this. How this is what expansion fan. How the flow pattern will be? The flow pattern for this will be like this. Suppose the flow field is what like this here. This is the flow field. So once flow will come and it will pass, so it will be like this. What about here? The flow will come and then it will go, because it's an expansion So it will go like this. Again, it will be parallel to the plane like this. Okay. So for this expansion corner, this will be what? Isentropic. And once I will explain expansion fan, that time all the property about expansion fan I will tell you. But here we'll have a isentropic, and this is what non-isentropic. Okay, this is for 1 marks. Always remember. So expansion corner, or now this is called expansion corner, but this one is called expansion. This is called a compression wave. Okay, this is the compression wave, and this will be the expansion. Okay, always remember this expansion wave also called as expansion fan. Okay, there should not be any confusion. And this one will be called as oblique shock wave, and this is the fan. Okay, so compression corner, in the sense, if you check when compression corner will be formed, so you measure from this. Just take this is the angle from here. Okay, from here, this angle. Okay, check this angle I am saying, and so say this is what alpha. This is what alpha. So if alpha is less than 180, if alpha is less than 180, then what corner will be created? Compression corner. And if alpha is greater than 180, then what corner will be created? Expansion corner. Remember this, they can ask you, okay, in examination. So this is very brief uh, discussion about the compression corner and expansion corner, when expansion corner will be created and when compression corner will be created. So for that, angle wise I have explained. So that's the reason, if you check for the compression corner, now why it is called compression corner. So you just think that flow is what coming straight. Okay, the flow is what going straight, and it will try to go straight again. This coming flow is what coming straight, and it should try to go straight only. But because of this corner here, this corner, here we have a corner like this one, so that flow is what again tilted towards. So it is what you can say, I will write here only, then it will be clear, because this terminology should be very clear, why it is called compression and why it is called expansion. I will write flow. This flow is, okay, this flow is turning towards. Okay, and this flow is what? Flow is turning away. Turning away. See, flow is what coming like this, and again it is going like this. It is going away. But here in this flow, the flow is what coming like this, and again it is turning towards the flow only. So it is turning towards the flow only, then it will try to compress it. Hence it is called compression wave. And where compression wave will get? Because of this compression corner. Because compression corner is what at this corner, that wedge is what turning towards the flow. So because the flow after the oblique shock, it will follow the parallel path to the plane of the object, hence it is that flow will also try to turn towards the flow. If it is trying to turn towards the flow, then it will try to compress the flow, hence it is called compression wave. Here the flow is what going like this, and the flow should go straight, it should go straight, but because of this wedge or object which is downside, so this flow will try to follow the parallel path to the plane of this object, hence it is the flow will be turning like this one. So it is actually turning ahead, turning away to the flow. I have written here turning away, so this is turning away and this is turning towards. Turning towards, hence it is trying to compress the flow. Turning away, hence it's trying to expand the flow. Okay, so in expansion velocity will increase, in compression velocity will decrease. Yes or no? That's the meaning of compression and expansion. Again, I will explain expansion fan when it will comes. But I think this much information is what sufficient here. Okay. So in short, I will write. Suppose this side Mach number is what M1 and this side Mach number is what M2. Similarly here M1 and this side M2. So what will be the relation for the that compression wave? I told you it is trying to compress the flow. So compression means what? Velocity will decrease. So velocity will decrease means what? Whatever the Mach number M2, it will be less than M1. Or you can say V2 less than. Okay, this is called compression because it is trying to compress the flow. What about the expansion fan? So this M2, because it is trying to expand the flow, hence that pressure will fall and velocity will increase. Velocity will increase means Mach number will also increase. So M2 will be greater than M1, or you can say V2 greater than M1. This is the biggest difference between the compression wave and expansion wave. So always remember this is very important. One more important thing I told you, compression wave is what non-isentropic, but expansion fan is isentropic phenomenon. Okay, so they will ask for 1 marks. Each and every points what I'm explaining, you please remember, because for one day exam or gate exam, if you write then this type of question for 1 marks they can ask any time. Okay, so one note I will give to you. What is the note? All naturally occurring shock in external flow are oblique shock. Okay, so whatever the naturally shocks occurring to the external flow, it will be oblique shock only. Okay, so you understood what is the compression corner, what is the expansion corner, what is the compression wave, what is the expansion wave, why it is called compression wave, why it is called expansion wave, what is the condition for compression wave, what is the condition for expansion wave, and what is the Mach relation. Okay, rest all the thermodynamic property will be changing, that we'll discuss later. All right, now I am stick with the oblique shock. Expansion fan I will continue after the oblique shock. Okay, all right. So now we'll go for this. Okay, fine. Okay. So all the thermodynamics property. Now we have to stick with the oblique shock. So I will give heading for oblique shock once again, and then we'll formulate oblique shock. How to develop the relation of between the all the quantities like Mach number and pressure, temperature, everything. So for that, I have to draw this diagram. With the help of this diagram, you can relate the quantity. So, so I'm preferring this John Deere induction, okay, compressible aerodynamics. So you can go through that textbook also for the practice and all. So this diagram also I have taken from the fundamental of aerodynamics induction. All right, I'm considering. Just say this is the oblique shock. Okay. So that oblique shock will be making angle from the horizontal, and that angle will be what? It will be beta. All right. I'm considering whatever the flow is coming. Okay, whatever the flow is coming, that will be called ahead to the shock here or upstream. So upstream, I will show like this is the flow coming towards the object. Okay, and then this flow should go straight. This flow should go straight, but it will not go. Why? Because that object is here, and let me draw the object also here. See, this object is here, and this object is what making angle, which is nothing but theta. This angle is nothing but theta from the horizon. So obviously this flow will also turn, and it will be parallel to the plane of the object like this. Okay, and what will be the angle here? This angle and this angle must be same, so this is also theta. This is what? Beta. All right, now it should not be any confusion. All right, this concentrate, so it will be very clear, easy to you. Now check this flow is nothing but velocity is what? V1 I can say upstream, and M1 is the Mach number for this upstream. Okay, then I will take the two component of this upstream flow. What are the two components? Normal and tangential. Normal to what? Normal to the oblique shock, and tangential to what? Tangential to the oblique shock. So where is the tangential? If this is the oblique shock, so I can draw one parallel line to the this oblique shock. So this is the parallel line to the oblique shock. So this will be tangential component of this upstream. This will be the tangential component, and perpendicular in the sense will draw normal to the oblique shock. So this will be what? Normal. And what will be this angle? This angle will be 90 degrees. Okay, this flow is like. So this will be called as tangential component. So I will write tangential component will be represented by W2, and this Mach will be MT2. Not MT2, it is MT1, sorry. Because it's upstream, so I will represent by 1. W1 and MT1. Now this is about upstream. Now this is what downstream. Okay. So this downstream will also have two components, which is perpendicular and tangential. Yes or no? So how to draw that? You can say, because this is the oblique shock here. Okay. And downstream will have the flow which is with velocity of v2. You can say this is v2, and this is what? M2. This is the actual flow after the oblique shock. Yes or no? Now this flow will have two component again. that is perpendicular and tangential. So this is the flow, and where is the perpendicular? This will be the perpendicular to the oblique shock. So I can say this perpendicular component will have, and this is the perpendicular component also. So we can say the velocity is nothing but u1 upstream, and Mach number will be m n1. Why it is, why m n1? Because it is a normal or perpendicular component. Similarly here, for the downstream, velocity becomes, you say, u2, and what will be the Mach number? It will be m n2, this perpendicular component. Okay, and where is the tangential component? So obviously for this flow, tangential component will be here only. This is the tangential component, and what is that value? It is nothing but W2 and MT. Okay, remember. So now hope if this diagram you understood, then it will be very easy to you. So I can say this is the upstream, and this is the downstream. This is normal component. This is also normal component for upstream, normal component, and this is tangential component, and this is also tangential component. Let me write down here. Tangential component. Okay, hope this one is clear to all. All right. Now, so check this. Now we can have the equation. We need to write the all quantity, and that quantities are like what is the M2, that is the downstream Mach number, and obviously upstream pressure is what here you can say P1, P1, rho 1, Mach 1 already I have shown you V1. These are the upstream value, and these are the downstream value, which is V2, M2, E2, E2. These are the downstream value. This is what oblique shock wave. All right. Now, so we'll find the value of P2 by P1, the value of P2 by P1, the value of rho 2 by rho 1, everything we have to calculate. So if you check here, if I will write what is the Mn1, so we can have here that sine beta. Okay, that sine beta. If you check, this sine beta will be Mn1 divided by M1. Yes or no? Why? Because if you check the angle from the horizontal, because this line and this line is what parallel to each other. Okay, this line and this oblique shock parallel to each other. So from the horizontal, what is this angle? This is what beta. So this will also be beta. So what will be the sine beta? It will be Mn1. This will be perpendicular, and this is the exactly 90 degree. So triangle law you can apply. It is a right angle. Yes or no? So mn1 divided by m1. That is the sine beta. So what is the mn1? mn1 will be m1 sine beta. Now we have to go for the calculation of first pressure ratio. Calculation of pressure ratio. What is the pressure ratio? It is P2 by P1. Yes or no? So what is the P2 by P1? From normal shock we know. What is that? 1 plus 2 gamma divided by gamma plus 1. Because now this oblique, why I have drawn this normal component, now you will clearly understand. Because this component, normal component to the oblique shock will be treated as a normal shock. Yes or no? Because this velocity, for this velocity component, this oblique shock will be treated as a normal shock. How? Check. This is the, you can say, oblique shock here, and the flow velocity is what, like, so this is exactly 90 degree. And what is the Mach number for this? It is mn1, normal component, and this is the oblique shock. So this will be treated as a 90 degree. It means it is treated as a normal shock. So you can apply normal shock formula here. P2 by P1 is equal to 1 plus 2 gamma upon gamma plus 1. Instead of m1, like in normal shock you had written m1, but this one will be mn1 square minus. Hope you understood this. It's very simple only. That normal component will be normal to the oblique shock. It is just like a normal shock. Because what was the normal shock? For the normal shock, flow was perpendicular. Same thing here also. But this flow Mach number is what, mn1. So I have written mn1. Alright. Now, what is the mn1? You know, so P2 by P1 is equal to 1 plus 2 gamma plus 1, and here in bracket it is mn1 is nothing but, here check, m1 sine beta, so this will be m1 square into sine square beta minus 1. So what is the P2 by P? 1 plus 2 gamma plus 1 m1 square sine square beta minus. Okay, you need to remember this here. This is very important. In short, I have given this formula. Okay, yes or no? Next, formula number 2. We need to write density ratio. That is rho 2 by rho 1. For the normal shock, what was the formula? It was rho 2 by rho 1 is equal to, what was the formula? It was gamma plus 1 m1 square. So now it will be mn1 square 2 plus gamma minus 1 mn1 square. Okay. So instead of mn1, you know it is m1 sine beta. So it is gamma plus 1 2 plus this one. This is the formula for rho 2 by rho 1. Similarly, this is the formula for rho 2 by rho 1 in oblique shock. Alright. The same way you can do for the oblique shock also. that T2 by T1 also. You can write T2 by T1, which is nothing but third one. What is third? Temperature ratio T2 by T1. How to get this? Again, it's a simple that same formula like you had written for the normal shock. So we will write this T2 by T1 is equal to 1 plus here instead of M1 you have to write Mn1 square minus 1 and in bracket 2 plus gamma minus 1. Remind it already I have given this formula last session, so directly I am writing gamma plus 1 instead of M1 Mn1. That's all. And you write Mn1 is equal to M1 square sin theta. Mn1 square is equal to M1 square sin square theta. Right? So this is also the value of T2 by T1. So in here, whatever the value I have given, you can use directly. Okay. So T2 by T1 is nothing but this value will be 1 plus to solve 2 gamma plus 1 M1 square and the beta minus 1, and this is 2 plus gamma minus 1 M1 square sin square beta divided by gamma plus 1 M1 square. This is what T2. Similarly, you can do for the what it is called Mn2 and M1 relation also. So the fourth number formula is relation between Mn2 and Mn1. So for the normal shock, what was the formula? In the same way, you have to write for the this one. So what was the normal shock formula? It was M2 square. So instead of M2, what we have to write? Mn2 square. Okay, is equal to 2 plus gamma minus 1. For the normal shock, it was M1 square. So you have to write Mn1 square divided by 2 plus, sorry, not 2 plus 2 gamma M1. So just recall normal shock formula. Okay, in the same way I am writing here. So in normal shock, it was 2 gamma M1 square. So I am writing Mn1 square minus gamma. So what will be Mn2 square? It is nothing but 2 plus gamma minus 1. Mn1 square is nothing but M1 square sin square beta divided by 2 gamma M1 square sin square beta minus gamma. This is the value of Mn2. Just like normal shock, instead of M1, I am writing Mn1. And why it is? By the diagram already I have explained. That's the reason I had drawn the diagram. So I hope this one is clear to you. This is the Mn. Now, just like we got Mn1 from M1, so again we have to find M2 value from Mn2. So for that, what we need to do? We'll see the diagram once again. Then we'll get that how to find that value. Yes or no? Check the previous diagram. So see here the same diagram, this one. If you say again, I can draw because this one little bit difficult diagram. So better again I will draw here. Okay. So hope this one is clear up to here. Now check. So the same diagram what you have seen here. If you check in the same diagram, this was the oblique shock. I said this is the horizontal, this angle is making theta, and this uh, from horizontal in this say this is the object, and this angle is what? Theta. Yes or no? So whatever the flow is coming from this side, the flow will be turning, you can say, this flow is what itself turning like this, and so for this only I had mentioned the perpendicular component will be here. This is the perpendicular component of this because this will have a Mach number m2. Huh? So this is the perpendicular to the shock. So obviously this component will be mn2. Yes or no? And check the angle how to get this whole angle itself. You can say what will be this angle. Check the whole angle is nothing but beta. This angle is nothing but theta. So this angle will be beta minus theta. Please check it. Beta minus theta. Check it. The beta minus theta. Beta minus theta. So this is what perpendicular component. So what will be the sine beta minus theta? Sine beta minus theta is nothing but perpendicular by hypotenuse. What is the hypotenuse? M2. Check properly. So now by this way I can calculate M2. Once we know Mn2, then M2 will be Mn2 minus sine beta. So this is very special formula. Okay, directly one time they had asked in here. This formula only they had asked. Mn2 divided by sine beta minus. Okay. So next is called theta theta m relation. So this is the one derivation I will say, but I will suggest here derivation not required. So I am giving this formula directly. You need to remember. Okay. This is what tan theta is equal to 2 cot beta m1 square sin square beta minus 1 divided by m1 square gamma plus cos 2 beta In GATE exam, whenever they have asked question based on it, they will give the table. Okay, they will give the table, so don't bother. I will tell you how to get the value from the table. Okay, theta beta m relation also they will give to you. It's your choice. You want to use table or you want to calculate the value with the help of calculator. Now virtual calculator available in the system itself, so it is very difficult to calculate. Earlier in 2014, 15 and before that, that engineering calculator was allowed that day. So, but now they are using the virtual calculator. So this type of equation it is difficult to solve. But nothing to worry, table they will give you, and I'll tell you how to get value from that table. All right. So now all the formula you have, like theta beta m relation, you have T2 by T1, T2 by T1, Rho2 by Rho1, everything you have now. So we'll stop here. All right.